This famous tower was slowly falling over, and engineers fixed it without pushing it upright. For centuries, Pisa's campanile leaned a little more each year, inching toward collapse. The mystery isn't that it leaned, it's why it didn't fall sooner. Answer: the ground under Pisa is soft, compressible soil, with water lurking below. From day one, the foundation was too shallow, about 3 meters deep on poor soil. Construction started in 1173, paused for wars and money, then resumed. The pauses let the soil creep. Uneven settlement made one side sink more, creating a tilt that fed on itself. Medieval builders tried compensating, stacking masonry thicker on the low side. That created a subtle S shape, but the lean kept growing. Stress cracks hinted at a future break. Foundations spread weight into soil. In Pisa, the soil squished and slid sideways. One side was softer, so it settled more. A small difference at the base multiplies at the top. As it tilted, the tower's center of mass shifted, increasing overturning moment. If the mass moves past the base edge, gravity wins and it topples. Groundwater made the clay weaker and more prone to creep under constant load. Settlement happened slowly, but relentlessly. By the 19th century, the lean exceeded 4 degrees. Engineers began precise measurements, tiny motions, big implications. The trend was clear, accelerating toward instability. Left alone, the tower could have crossed the tipping line within decades. Pulling on the high side, it risked cracking the brittle stone. Adding weight to counterbalance only pressed the soft soil harder. Boring or injecting grout could worsen uneven stiffness. A stiff ring can push the problem sideways instead of solving it. The lean kept increasing, over 5 degrees by the late 20th century. Cracks in a shifting center of mass raised alarms. In 1990, the site closed to the public for safety. An international team formed to save the tower without straightening it completely. They needed a gentle method. No pushing, no sudden moves. Any misstep could trigger a catastrophe. The breakthrough: under excavation, removing small amounts of soil from the high side. Engineers drilled shallow, angled holes just beneath the foundation. They removed soil in millimeter increments, then paused to measure. After each step, monitor, wait, confirm stability. Temporary counterweights managed risk while under excavation progressed. As soil left the high side, the tower rotated back, fraction by fraction. The soil reformed arches, redistributing stress without shock. Redundancies, anchors and restraints, stood by in case of sudden movement. The trend reversed. The lean shrank measurably. Continuous monitoring kept motions within safe limits. Then came the critical phase: remove just enough soil, no more. Each gram changed forces on a 14,000-ton structure. The tower eased towards stability without a push. Net correction, roughly 40 centimeters at the top, about 0.5 degrees. Bores sealed. Monitoring continued. The ground restabilized. In 2001, the tower reopened, safe for visitors. By removing soil on one side, engineers made the tower stand straighter, and likely safe for centuries. Elegant engineering fixed the foundation, not the facade.